really amazing workshop about softwares, because I really think that yeah, that was missing in the community. So I really enjoyed it. And so in my brief talk, I will discuss about the SimSOFT, which is our physics engine from hybrid soft robots. I'm Stanislao, and I came from University of Naples, Federico II. And so the goal which motivated our work in the previous years was develop a generical framework for both modeling and simulation purposes to be as accurate as computationally efficient possible for allowing the simulation of rigid and soft robots. And the pillars on which is based this framework are basically two. One is differential geometry and the screw theory, and another one is quadrant rod theory and the finite element method. The framework can accommodate the modeling of rigid bodies, of soft continuum bodies, and also hybrid soft robots. So what we call with what we refer to with articulated soft robots, which can be composed by rigid or continuum links, articulated in a serial and parallel kinematic topology, as the structure that let's say academic structure that we see in this slide. This is the general picture about the framework. So we are able to model rigid bodies, which are just modeled as ordinary differential equations. The partial differential equations of our continuum body is discretized using finite element methods to obtain ordinary differential equations, and we take care about the presence of joints inside our robotic structures with a set of algebraic equations that we build that will be included in the general equation of motion of inarticulated systems that takes the form of differential algebraic equations. Just briefly overview about mathematics behind the simulator. So rigid body, so very simple description. We have a local frame H, which has 6 degrees of freedom, which belongs to the special equilibrium group 3, which is attached to the center of gravity of the rigid body. And the kinematics and dynamics equations are described as standard in a very standard way. So, starting for the continuum body. So as also other kind of software, let's say Pielastica, that a really amazing presentation we saw before. So we use Kosterov beam for describing our soft continuum arms. And why this? Because we are interested in soft robotic arms which has one dimension which is predominant over the two others. And so Kosterov rod theory is a nonlinear theory which can allow the accounting of large motions without approximation on kinematic variables. And the assumption for Kosterov rod beam is that in this case a soft robotic arm can be seen as the continuously assembly of bidimensional cross sections which moves on a three-dimensional curve according to infinite rigid body transformations of the cross sections, and these infinite rigid body transformations are defined by the internal law of deformations. And here just the continuum formulation of a continuum arm in this, which is actually the Kosterov rod theory using a geometric framework, so using the screw theory. So we have the deformation field and the velocity field, the material constitutive law, the compatibility equations, and after the static and dynamic equations of motion. So we have to discretize for sure the continuum equations, and in this case we use a finite element method, which involves helical shape functions. So for each element in which we will divide our manipulator, we have one, let's say, start node, one end node, plus analytical check functions which relates which interpolates the two nodes. And the important stuff is that for each element in which we will define our manipulator, we have constant deformations. And with constant deformations, we mean all the components of the deformations to be constant. So the bending, the shear, the torsion, and the axial compression strains. And these is the discrete formulations. So the kinematics that in this case is described by a simple relationships which make use of the exponential mapping, which relates the deformation field with the kinematics, with the h as a function of alpha, which is the material abscissa. And after the differential kinematics, which relates the velocity of the along the manipulator with the derivative of the deformation, and as well as the static and dynamic models. To take care about inarticulated systems, we have to introduce the joints, and in this case, in this framework, screw theory based framework, we will take care about the presence of the joints by this HJI element, which is an element belonging to the Lie subgroup of the special Euclidean group 3. And within the framework, we can accommodate both rigid joints and flexible joints by using, in the latter case, a stiffness and a damper within the joint itself. We can accommodate the modeling of all the 6 Lauper joints: revolute, prismatic, screw, cylindrical, planar, and spherical joints. And the equation of motions of a constrained systems are as follows. And with respect to the previous one, we take care about the presence of the joints via a set of algebraic constraints. So for each joint, we introduce 6 algebraic constraints which say which is the direction of allowed motion within the mechanism. Here some benchmark, very simple benchmarks also from previous literature. We have for validating the beam, let's say, element, the so-called Princeton experiment, which is a standard example to validate beam theories, because here we have a slender beam where there is an end load F with acting on the beam with different intensities and different lines of actions, and these loads induces within the beam a very highly nonlinear behavior where bending and torsion are coupled. And we have measurements at 4 cross sections along the beam, and we have compared our simulation results with the experiments that are available from the literature. And as we can see from the plot, the simulations matches the experimental values. Here we have just the error, the percentage error values, and along the length of the beam for each value theta, which is the line of action of the forces F. After, for having also a benchmark on the articulated system, we have used a special flexible manipulator which was present at Georgia Tech, and the work by Arthur Kivila. And this is a simple flexible manipulator with 2 links and 3 joints. And we have replicated the experiments presented in this paper, where, for instance, we have replicated motions which is applied at joint level and for 3 maneuvers of the system. And also in this case, as we can see, there is a good matching between the simulations and experiments. What about the usage? So for now, the simulator takes as input, an input file which where the user is going to describe the geometry of the system and the behavior of the bodies. So if they are rigid bodies, either soft bodies, and for sure, if you have a rigid body, you came up with including the mass of the body and the inertia properties, while for soft bodies, since we deal just with the monodimensional elements, we need mass and stiffness matrices for the element. We can include the joints, and so the low pair joints that we have described, and we have the animation can be done both at joint level, so a classical joint motion, or either we can have forces applied at a certain point, at certain nodes on our system to generate the simulation. And so with this input file we start the simulation, and in output we have classical kinematic variables, position, velocities and accelerations of nodes and of joints, the forces and torques and boundaries and joint locations, as well as stresses and strains within the elements. Some examples that we have done, mostly based on simulations from on just simulations. In this case, we will see here on the upper part of the slide. This is the TARM, which is a highly redundant flexible manipulator, which is available at RACE UK AA, and it's a standard manipulator which is used for remote manipulation of within nuclear fusion reactors for assembly procedures. And in this case, the flexible, we have just modeled the system as rigid bodies with a flexible payload, which is a flexible payload that was designed to study the effect of flexibility within the remote manipulators during a remote maintenance operations. And here we have on the bottom part another mechanism. In this case is a serial parallel mechanism, which is known in the literature as the tricept. And this is also another mechanism that is used for remote maintenance applications. And in this case we have also rigid bodies and flexible behaviors of the actuation units. This is just to explain the, let's say, the capability of the framework also on highly articulated structures. More, let's say, flexible and soft continuum structures. So here some really basic simulations about a soft bending actuator or a continuum robotic catheter, which is composed in this, which is modeled in this case as a two elements with helical shape functions on each element. In the recent time, we are also developing a new graphical user interface, which can be more interactive and immersive for the user, because we have in mind applications as a teleoperation, for which an immersive environment in which the remote user can operate will be of really great value. And this is a very ongoing work. This is just a simple new interface for, in this case, a soft articulated robot. We will see that we can import the files directly from the backend. We can play the simulation, we can stop the simulation, we can see in 3D the motion of the system. But this for now is just made with very simple elements, because in the next work we are also including more refined and the possibility to import also STL files as input. Here, just another example on a continuum body, and also in this case we can see the continuum element, which is from is a three-dimensional perspective, and so
2 minutes left.
Sorry?
About 2 minutes remaining.
Okay. And yeah, this is just my conclusion. So the framework, I presented a modeling and simulation framework, which is based on geometric theory, the cost-related models, and the finite element method. And we have the possibility to model robots, which are composed by rigid and continuum bodies, which are articulated in a kinematic chain. So the framework can be useful for continuum robots, for flexible manipulators, or also for articulated hybrid systems. And the backend is developed in C++, and the front end for now, the newest version in Unity 3D. So what we are developing in the next future, so to enhance our GUI for using it in a remote teleoperation framework. And another piece of work that we are really interested in is developing a tool for conceptual design of hybrid soft robots based on the environment in which they can operate. So thank you very much for your attention.
Cool. Stanislao. Cool. So does anyone have any questions?
We have a question here.
Cool.
Thank you. Thank you for the presentation. I got actually quite a simple question. First, is all the code and so on available, open, and can that be shared? And the second point I had in mind is actually it could be related to the roundtable at the end of the day, but where several teams like to develop very similar tools. We are in the SOFA community. We are having GOSRA. We are having Timoshenko co-beams, FEM approach for continuum mechanics. I was wondering if there would be ways to like collaborate and avoiding, re-implementing things again and again, for also having more stable codes and more tested codes, validated codes, and so on. So maybe first the main points, maybe availability of what you implemented?
Yeah, the code is not, we didn't make the code available for at least for now. So because it's still, it's always in progress, and so we are very few people that works from our side on these. So also to have also an open source framework, you have to maintain it, and you have to do a lot of work. And now, for now, we are not yet ready for doing this. And the second point is for sure we are available for collaboration and also for testing implementation of some models also in different simulation, for sure, simulation environment, I mean.
I think it would be interesting to discuss more collaborations, and at Napoli we are working also with Fanny. I'm gonna pronounce that very badly, but Finucello, or so I don't know if you know her, but yeah, could be a vector of collaborations as well. But yeah, thanks a lot for first for the nice presentation, all the work you already did and implemented, and the reply, the answer. Thanks.
Thank you.
Cool. All right.